what we've used so far in the previous examples for memory addressing was the simplest form, which we have an address stored in a register, and we just tell memory to return us the value of the location stored in a register. Now we're going to see, and that's what we call an addressing mode. Now we're going to see the complete addressing modes supported by x86. Okay, so these is how addresses are used for accessing memory in the move instructions, and we saw a lot of them in the previous examples. Okay, so the most general form of addressing mode in x86 is the following form. Okay, we have D is a constant displacement, something that's added to the final address. Okay, and this is a constant that has to be 1, 2, or 4 bytes. That's a constant displacement. That doesn't mean that it can be only off by 4 bytes. It means that the displacement distance itself has to be a value of 1, 2, or 4 bytes. Okay, so now the other parameter here, RB, is a base register. It's called a base register because we're adding to that reference point. That's the base register where our address starts to be computed from. Okay? RI, also called the index register, is used for things like arrays. That's why we have a multiplication here by the contents of RI. And that's multiplied by a constant called S, which is the scale. Okay? And this value can be 1, 2, 4, or 8. Why those numbers? Well, those numbers because we want to efficiently support arrays of values of these sizes. Okay? So, by the way, there's many special cases on how to use this complete addressing mode. For example, if you just use in parentheses RB, RI, the final memory address is going to be the contents of RB added with the contents of RI. And that's because in this case, S, variable S is just set to, the constant S is set to 1, the scale is set to 1. Now we can also use D, RB, RI, and that's just going to do RB plus RI plus D. And the scale here is just set to 1, that's the special case. Okay? And also, you could have no displacement at all, you're not adding anything, right? So this displacement is effectively 0. Okay, so it adds RB with the scale multiplied by register RI. So let's see some quick examples here. We have two registers in our example, EDX and ECX. EDX is set to F000 hex, and ECX is set to 100. Okay? So now we're going to be exercising all of these addressing modes here. Let's start with the first one. This first one here, our D, the displacement, is 0x8. And we're adding this to the contents of EDX. So are we going to see that? Well, that's the value of EDX. That's the constant. The final address is just an addition of these two. Okay. Now, the next one is using this form here, right, which is just going to be RB plus RI. In this case, just EDX plus ECX. That's what we get here, F100. Now, the third example here is using a scale factor. Okay, so and what it's going to do is it's going to get EDX and add it to 4 times, because we had 4 here, ECX, which is 100. So in the end we get F400. So now the final example here is D is set to 0x80. We do not have RB, so RB is empty, but we have RI and we have a scale too. So what is this going to do? Well, it's going to do 2 times the contents of EDX, okay, that's here, added with the displacement, and we get the final address 1E080. There is an instruction in x86 called layout that gets a source. So its source operand is an address mode expression, is any of the expressions that I just showed you. And so what this instruction does, it evaluates that address mode expression and puts the resulting address into the destination operand, into the destination register. For example, if I use this, what is it going to do? Well, EAX is going to get, this is going to give us EAX equals EDX plus 4 times ECX. Isn't that cool? So, and you can use that to actually compute addresses, right? So to compute addresses without a memory reference. So if you have this in your C code, Gaetano showed you this when he talked about pointers. Right? What you want to do here, you're going to get the address of the ith element of array X. Okay? Since you just want to get the address, you're not doing the memory. You're not doing the memory access. So in this case, you're going to be using this layout instruction. But this instruction it can actually be used to compute any expression of the form, any arithmetic expression of the form x plus k times I. Now I'll tell a bit about some other arithmetic operations, and we're going to put everything together into a larger example. Okay, a larger example. So here we're doing, we have a bunch of instructions. The first one does a arithmetic addition. Okay, so it takes two operands, a source and destination, and it gets destination equals destination plus the source. Okay. The sub is very similar, except that it does subtraction. And IMO, same thing, except that it does multiplication. So now we're going to see instructions that actually does shifts. So just shifts bitwise. Okay. So SALL is doing a shift arithmetic, and it's called shift arithmetic because it preserves the sign bit. It does something special with the sign bit. Okay. So this SAL means left, so that's why it's shifting to the left. So it gets the destination, gets the destination value, shifts left by the source operand, and stores it back into the destination register. Now SARL does the same thing, but now just R because it shifts to the right. Okay, and this SHRL is shifting to the right. Okay? Except that this is shift logical, meaning that it does not do anything with your sign bit. Okay? So the XOR L instruction, it just does an XOR of the destination with the source and stores it back to the destination, and does a bitwise and OR does a bitwise OR. Okay? So then watch out for the argument order. That's actually very important. Okay? Because the argument order affects your result, especially for subtraction. So and note that there's no distinction here between signed and unsigned int. Why is that? Well, it's because remember that if you use 2's complement, you can do arithmetic without regards for the sign bits. Everything just falls out of that. Okay? But note that you do have to worry about whether you're doing shifts arithmetic or shift logical because of the sign bit. Here's some other arithmetic operations. This is a unary instructions because it takes a single operand. Inco just increments by 1, deco decrements by 1, and then nego just changes the sign bit. Okay, just changes the sign. And not just a bitwise not of the contents of the register. And now you should look at the textbook for more instructions like mul and so on, division and so on. Okay, so now let's put everything together in an example that uses layout and some other instructions as well. Okay, so recall that now we have the setup that's just saving the stack pointer, and then finish is just restoring the stack pointer and returning. Okay, this is the C code that we are implementing here. Let's see how this works. First of all, this is our stack, so you know where our parameters are. We have 3 parameters. Okay, so this is IA32. That means that the parameters are stored onto the stack. What these 2 instructions here are doing, they're just reading X and Y and putting it into EAX and EDX. Okay, and that's what this one here is doing. This one is using the layout this is the layout instruction. What it's going to do is just going to add EDX with EAX and put it in ECX. Okay, recall that layout just evaluates expressions of any expression looks like an address expression. Okay, and now we use it again here when we're multiplying. So now we're executing this statement, and this layout, this instruction gets EDX, okay, and adds it with 2 times EDX and store it in EDX. Okay, So that's why we get EDX equals y plus 2 times y, which is the same thing as 3 times y. Now we're shifting arithmetic left here by 4. What does that mean to shift by 4? 4 bits is the same thing as multiplying by 2 to the 4, which is 16. That's why now we get 16 times 3 equals 48. That's why we're now effectively storing 48 times y into EDX, because before we had 3y multiplied by 16. Now we have 48 multiplied by y and stored into EDX. Now, and the next instruction now is just, what is it doing? It's implementing this one here, okay? So it does T5 equals T3 plus T4. But what it did was it just inlined this one. It's executing this one together as well, okay? It's just putting it here, okay? That's why now what we're doing is 4, that's this parameter here, adding 4, okay, which was the 4 here, with T4 that was computed by the previous instruction, and adding it with X that just happens to be stored in EAX, and then storing back in EAX. And then finally, we are in this instruction here. This instruction is just implementing the final step in our function. Okay, so things to note here is that note that the instructions are in the different order than what appeared in the C code. Okay, so you see like this orange instruction happens to implement and relates to these two instructions in C code, these two statements in the C code. And also, green comes before blue in C, but blue comes before green in the assembly code. Okay. And also, it's interesting to note that some expressions require multiple instructions, and some instructions, like this one that I just showed here, covers multiple expressions. Okay? And you get the same exact code when you compile this. Why is that? Because the compiler is going to have to create temporary variables anyways. So let me show you another example now. This example is implementing this logical function that evaluates all of these, that executes all of these expressions here. And again, here what this is like the previous example, we're just reading a parameter from the stack. Now this function has two parameters, x and y. This instruction is just loading the x parameter, which is 8 from EBP, into EAX. Okay? And let's see what the first instruction is doing now. This first instruction here, this XOR, is implementing this statement here. And look how interesting. This instruction is an interesting example because it has a register operand as well as a memory operand. Okay? And this memory operand happens to point to where y was located. So that's why this instruction implements x XOR y. Now, this instruction here is just shifting EAX right by 17 bits. So it's implementing this expression here, this statement here. And we're shifting right, so it chooses the compiler chose the shift right instruction. And finally, this instruction here is implementing these two statements. But there's something interesting here going on, right? What the compiler did was note that this expression here is a constant expression. But instead of inserting instructions to evaluate that, the compiler evaluates that at compile time, produces a single number that represents that instruction, that represents that statement, and uses it in the instruction. So you don't have to do this in during execution time. We just do it at compile time once because we know it's not going to change. Isn't that cool? That's going to be much faster.